Yeah. Good afternoon, everybody. Welcome to near real-time data uses for Earth science and space weather applications. We've been doing this session for about, I guess this is our third year now, and it really tries to link a lot of the science that has gone into the development of systems to applications that require low latency products from satellites or other types of instruments. We have 3 oral sessions today, or 3 oral sessions within our area here. The first one's today, and this is going to be on social and mass media. We have 2 more tomorrow at 8 and at 10 in Moscone West 220, followed by a poster session. What I'd like to do is say that we'll have Kevin Ward here, Juan Rodriguez, and Na Chung, and they'll be presenting this afternoon. The need for near real-time data is apparent by the number of submissions we get to this session every year. We have gotten now, I guess, this is probably the 2nd year running, where this particular, we've gotten the most things in the IN framework. Anyhow, let me now welcome Kevin Ward to the stage to talk about News at 9. Thanks.
Good afternoon. Thank you, Kevin. My name is Kevin Ward. I'm the team leader of NASA's Earth Observatory group. We are based out of Goddard Space Flight Center, and I'm here to talk to you about how we utilize near real-time data and how our approach to providing near real-time imagery to the mass media is really the construction of an ecosystem related to this whole process. And so I'll kind of explain the history of how we've gone about our business in providing these kinds of images. Oh, thank you. The Earth Observatory was established in 1999. Our purpose was to be kind of a web-based magazine with the idea of providing a central point for information related to the Earth observing system and the launches of its initial spacecraft, the Terra satellite. At that time, there was not a kind of a single point of information for topics related to the background, the science topics related to the instruments, how they were going to be used, et cetera. And so it was the impetus to provide that resource that led us to develop the site. And our goal is to stimulate interest and awareness in NASA products, NASA science, and NASA imagery. Keep doing that. So in the last 13 and a half years, we've produced over 11,000 image-driven stories. That includes our image of the day image and story, plus natural hazards or event-driven imagery. We've also produced over 370 feature articles and fact sheets. Feature articles discuss how NASA research is used, how NASA data is used. Fact sheets are more about core science topics, whether they be phytoplankton, remote sensing, the carbon cycle, et cetera, et cetera. So we have a rather substantial catalog that we've developed over the years. No, it just still didn't come out. In 1999, when we started, it was pretty much all we could do to manage an image of the week. The systems that were online and had data available consisted really of CWIFs, Landsat, GOES, and AVHRR. And even then, lots of data was not easily accessible. And so providing any kind of quick turnaround was extremely difficult. That started to change that year with the launches of the Terra satellite and also Landsat 7, which came online that year. In 2000, we had the first light images from the Terra missions that you see listed there. We were finally able to get up to speed, up to an image of the weekday. There were more data available. There were more scientists looking at data constantly and communicating with us. Our big challenge at that time, however, was the fact that a lot of the data was held in offline tape storages. So identifying, locating, downloading, getting the data was a very time-consuming process. It did not allow for easy exploration. And as a result, our timeliness, or our near real-time timeliness, was not near or real-time. And lots of times, within a couple weeks or a month, we were able to turn something around just because that's the way the data systems were set up. In 2001, 2002, we finally got to image of the day. So there was enough data online, getting out of the tape archives, getting into online repositories, and also we were greatly aided by the establishment of the MODIS rapid response system, which was originally created to do real-time or near real-time fire monitoring using MODIS data. But because of its capabilities, also gave us true color, false color, pretty much near real-time data. And so we could see events as they were coming up, or if we read about an event in a news story, we could hunt down imagery from that. And so we're finally at this point starting to realize kind of a near real-time turnaround. In 2003, I'd say we finally got over the hump. Things were really starting to click with near real-time delivery. There's more data from more sensors. Other satellites have launched. The Aqua satellite has launched. And more is available online. I'd say, I'm not 100% accurate, but I'd say that most of the data is finally out of the deep archives and accessible. And that really gives us the opportunity to turn things around relatively quickly. So for example, on the left here, we have a MODIS image showing smoke from California wildfires in 2003. And we have a really nice opportunity here to pair it with another near real-time remote sensing source, and that is astronaut photography from the International Space Station, which is the photo on the right. And so relationships that have been built through our comrades at Johnson Space Flight Center with colleagues in the MODIS community and the science communities are really helping us to turn these resources around and make them available for the media. So one of the things that's really benefited us and maybe the greater community is looking at near real-time and free data, having data available online, lowering the hurdles to data access, providing browse interfaces that give any user the ability to browse through these vast collections of imagery. For some very notable examples that we use every day, as I mentioned, the MODIS Rapid Response at NASA, but also GLOVIS and the Earth Explorer through USGS, which gives us a lot of access to Landsat, ASTER, EO1 data. And those interfaces allow all sorts of other people to come in and start retrieving imagery. It's really cutting out the middleman. We don't need to go and identify the source of a particular data set or whoever has that sitting in their personal repository. Most everything we need is available online. And it really promotes the exploration of data. We can now go and look for anything we want without any restrictions as to time lag or expense. And so I have a couple examples where this is really played out to our advantage. As I mentioned, Landsat. In 1999, Landsat scenes cost about $600 a scene and took about 1 to 2 weeks to acquire. Well, as a result, that made any kind of exploration of data or retrieving imagery that we think might work, the cost is quite prohibitive. And the time turnaround just really doesn't work for the kind of events that we're looking to visualize on the Earth Observatory. Turn that up a dozen years to 2011, in a particular case where we have flooding in the Mississippi River, which was quite a large event and over a rather large area. And so it really gave us an opportunity to highlight imagery from a lot of different sensors and and just pump out a lot of different images. The images are free now. The images with some partnerships, can be turned over in as little as a couple hours, definitely within a day. And as a result, that gives us the chance to get these things out to the media, and that's how they appear on places like CNN, who will pick up this particular image showing flooding near Memphis, Tennessee, showing a before and after picture of the flooding. The media want these things, are interested in showing these kinds of images, but they want them now. They don't want them in a couple weeks. They're going to tell the story. I mean, they are reporting the news. They're going to tell the story. And if they can tell the story using NASA or other science imagery, then that helps create that attention and that awareness that's really important for getting that kind of word out to the public that, yes, we at NASA, we take images of the Earth. We don't just send things to Mars or to the Moon. Another great success story that's really worked well with us is the Earth Observing 1 satellite that was launched in 2000, and particularly one of its instruments called the Advanced Land Imager, ALI. But when it was launched, I mean, EO1 was a very research-oriented instrument, and the data access really required, like I mentioned before, that connecting with scientists and saying, well, what have you got? Or relying on scientists to communicate to us. Oh, we found this really nice volcano eruption, or we got this really nice shot of a dust storm, et cetera. And so it really required scientists to be proactive to kind of alert the outreach or the media community as to what they were seeing. But come up to 2008, and they developed a system for ordering data. They developed their own system for ordering data. They also developed an internal system which allows you to schedule acquisitions. So, for example, on our team, we are combing the news media all the time for stories related to natural hazard events, whether it's fires, flooding, what have you, volcanic eruptions especially with EO1. And if we see something, they've given us the ability to go in and say, we'd like to schedule an acquisition of this location, at the next priority. There's many scientific targets going on as well in the scheduling process. But by giving us that ability, that allows us to choose our targets and choose what things we can produce to the media. So, for example, we have an image here of an area in the Red Sea. This is from 2007. And we started hearing news reports in 2011 of fishermen reporting a volcano erupting in the middle of the Red Sea, and that there was an island that was starting to form. And so once we got some coordinates for that, we were able to make the request for the acquisition and then get the image that shows that exact event going on. Well, these kinds of things aren't necessarily, run-of-the-mill for the science, but they're very important for the outreach and, again, getting that attention and awareness from the general public by getting these kinds of news events out there, and not just the high-level big events like hurricanes. We're talking, maybe very, very localized events that may not warrant attention from the public at large, but maybe there's enough people in this case, the volcanic community, or people who are interested in volcanoes in general. It's a very good resource for them in getting news out and, again, creating awareness. Near real time for the media, and I'm just overemphasizing this, near real time means media attention. Media, like I said, media want it now. They're not going to wait. They're going to tell the story. And that media attention means the support and appreciation from their viewer publics. So when we get imagery and it gets put out on CNN, for example, showing flooding in Thailand, this is a story they're going to tell. And whether it's a person, a talking head sitting on the ground in Bangkok reporting on the flooding, or other means, it's much better, or at least from a NASA outreach perspective, to have our name on an image showing the extent of the flooding. Again, this kind of imagery, these kinds of things are just part of telling the story. There's that inherent value in seeing things from space, and communicating that to the public is very important. So like I mentioned at the beginning, we kind of view near real-time as kind of an ecosystem of practices, because it's not just about the near real-time data systems. It's about a whole process that involves our data visualizers and data processors. It involves a lot of relationships with scientists, or knowing who the content specialists are or the event specialists are for a particular type of event that we're trying to visualize. It's knowing where to go for interpretation of that data. We've gathered quite a bit of experience over the dozen years, but there's still obviously a lot of scientific experience out there at the NASA centers or the academic centers who know the specifics of maybe what's going on in a particular event, and it's learning to exploit those relationships so that we can tell the story. Lots of institutional knowledge. And then packaging materials up, making sure that we're providing imagery that are basically digestible by the media, providing things that have been color corrected that look really excellent, providing labels, but also providing the high resolution so that if an end user wants to use them and provide their own labels, they're able to do that. So it really is this whole ecosystem approach to near real-time production of imagery for media consumption. So what I just want to say for anybody who happens to, in the spare time, wanting to develop a near real-time data system, the things we really need are that rapid availability, a browse. It seems something that should be second nature, but browse functions sometimes leave a lot to be desired because you need to be able to go in and browse an entire collection of data relatively easy to do the kind of story combing that we're doing. Active support by science teams. Much of what we do is not possible without having these relationships with the science teams. Very, very important. And of course, just streamlining the path for use through the rapid availability, through ease of access of the data, through ease of downloading the data. And when it all comes together, it allows us to do things, create some really spectacular products. So for example, this one is showing Hurricane Sandy as it came aground, and this is using the Suomi NPP VIIRS day-night band imagery, which in a shameless plug, you'll see a very cool new city lights image tomorrow at our press conference at 10:30. But it allows us to produce these kinds of things that are easily recognizable by the general public. They are current. They are pertinent to their lives, especially in the case of Hurricane Sandy, and they are really cool images. And that's the kind of things we want to continue to produce and get out to the media as quickly as possible. And then lastly, it also enables application developers to, because it gets into our system, it provides us the ability to provide feeds to applications like this one, for example, which is called XWeather, which basically takes our images and highlights them, repackages them, and again, contributes to that awareness of NASA data, NASA science, and just in general, how NASA goes about observing the Earth. And thank you very much.
Oh, we have time for a question or two.
Or not.
Up front.
Oh, Michael.
Kevin, I know you're providing data to the news media. What percentage, or can you say, do you actively go out and promote those images to the news media, or do you find the news media coming to you and saying, hey, there's this event, what do you have?
Right. So the question is the media coming to us, or are we going to them? And anymore, it's more they're coming to us. We've established ourselves well enough that they basically follow our RSS feeds or us on Facebook or Twitter. And now, again, with these social media outlets, the syndication of that content is even more rapid. And so we find that we don't have to go after them as much to report them. But that being said, we also make sure that there's There are individuals that have communicated us with in the past, and so we communicate with them. We also alert NASA headquarters if there's something that's really fantastic and really late breaking that we're putting out, so they can add it to their Twitter and Facebook and utilizing those social media streams to get the word out. All right.
Thank you.
Thank you very much.
Next, we have Juan Rodriguez, and he's going to be talking about NOAA people-empowered products.
Green, yes. Yeah, that's the, yeah, and hopefully it should pick up on the movie. If not, we'll be fine.
Just use this clip.
Oh, right. Just the right?
Yeah, or you can use this if you're more comfortable.
Okay, great, thanks. Well, good afternoon. I work very closely with all the authors on the list in the NOAA National Geophysical Data Center in Boulder, Colorado. Stefan Kodrescu, the first author, is a student at Fairview High School in Boulder. He's doing excellent work for us. Of course, he's in school right now, so he couldn't be here. Janet Green, Dr. Janet Green of NGDC, was hoping to make this presentation, but she couldn't attend the fall meeting, so I'm grateful that the conveners are allowing me to give this presentation. I'll be talking to you today about a new effort we have called NOAA People Empowered Products, or PEEP, combining social media with scientific models to provide eyewitness confirmed products. And if there's one takeaway that we'd like you to go away from this talk with, it's that essentially we're seeking with this effort to transform our public users from basically passive users of our data products to active participants in the improvement of our data products. That didn't work. Let's try that. Thanks. So an outline of the presentation. First, I'll provide an overview of our standard operating procedures when it comes to producing data products. Then go into the inspiration for our work and the basic concept of a PEEP. Finally, I'll talk about our auroral PEEP, which is what Stefan's working on right now. Both our successes so far and the issues we still face there. And finally, conclude with other possible applications. So our standard NOAA operational products are driven by instrument measurements and numerical models. In the case of space weather products, which is the area I come out of and that the authors on this talk work on, we're really reliant on instruments on satellites. And in particular in the area the area of measuring aurora, measurements are often sparse. They're certainly expensive when it comes to satellite-borne instruments, and these models are not 100% accurate. The method we're following here for addressing these shortfalls is to make use of an abundant source of measurements, namely millions of eyewitnesses globally viewing weather or other events, and incorporate these user eyewitness reports through social media or other methods into NOAA real-time and retrospective. I like to emphasize the retrospective aspect of these weather products and alerts. At this point, again, we have a prototype which has been developed. It uses Twitter reports of visible aurora that is visible to the human eye, and combined with Google Earth, along with measured data and a model of the aurora to enhance the product we provide. Again, I'd like to emphasize there's general public interest in the aurora, so I'm not talking here necessarily about scientific users or scientific peers, but the general public. And the benefit to users, not just the general public, but I think also scientists eventually, would be more reliable, accurate, real-time validated products. So the big idea here is to combine a physical model, measurements, and user reports for an improved final product. The physical model would be any model predicting an aspect of weather that outside users may actually observe. for example, the aurora. Measurements would involve any direct measurement of the phenomenon. In this case, these are the auroral electron and proton measurements measured by the NOAA polar orbiting environmental satellites. And finally, the user reports. Any report from outside users, such as using Twitter or internet forums. Now, the inspiration actually comes out of a great success story at the U.S. Geological Survey. USGS in Golden has implemented a tool that uses Twitter to rapidly detect earthquakes on a global basis. Sometimes this is faster than the seismic measurements that, of course, they use. The tool searches Twitter for earthquake in different languages. An alert is issued when the instances exceed a certain threshold. The earthquake is located by the geographic information embedded in the tweet. Short narratives by the tweeters provide qualitative indication of shaking. You can imagine what some of those might be like. And this provides, and this is actually particularly important, a very nice enhancement to the capabilities in that it provides a starting time and location to manually search events that otherwise, because of their low magnitude, might be missed by automatic seismic systems. So the auroral PEEP prototype at this time is a combination of a numerical model and user reports produced in a combined output that is a Google Earth display. The numerical model is called Ovation Prime. It's based on work by Pat Newell and others at the Johns Hopkins University Applied Physics Laboratory in Maryland. It's a statistical model of the aurora. This model is based on decades of observations of auroral electrons and ions precipitating into the upper atmosphere and causing the light displays that we're familiar with. These observations have been made over a period of decades by the defense, by instruments on the Defense Meteorological Satellite Program, or DMSP. And Pat Newell put together the statistical model that predicts, essentially is able to correlate the location of aurora in latitude and longitude with measurements made by, in this case, the Advanced Composition Explorer, or ACE satellite, at the L1 point ahead between the Earth and the Sun, and specifically correlated with the magnetic field in the solar wind and the velocity of the solar wind. So it's a very good correlation. It's a functional response it's somewhat complicated, but it works very well. This was designed as an auroral research tool, and it has been modified to run in real time at NGDC to provide the public with a prediction of when the aurora is visible. Now, this is a statistical model. It tends to smear out the actual location of the aurora, and so these PEEPs can provide precise location, maybe a little more precise at times than the smeared model. Again, user reports will come from Twitter. The original implementation searched for generic terms, but this failed to find enough meaningful events, so we're looking at directing users to tweet to a dedicated account in order to refine results. A significant number of events are expected. I mean, this implies that essentially we have to train the public to do this. We're highly optimistic that this will work because, in fact, the legacy NOAA auroral products are by far the most popular products put out by NOAA in the area of space environment and aurora. And so there's a high level of interest, and we think that we can, again, this is a way of essentially enhancing the role of the public in these products with this, by telling them to use this website. And then finally, the combined output of Ovation and the tweet locations are translated into KML files displayed in the web browser using the Google Earth plugin. And KML is good because it provides flexibility for adding additional data. For example, cloud cover. I mean, if you hope to see the aurora and it's cloudy, you're not going to see it unless it's really bright, and then it's still not very impressive. So right now it's currently running in a non-public demo mode. Obviously, we like to bring it out into a beta version, add the ability to show other measurements. For example, adding the measured auroral fluxes from our satellites. Include educational material, allow users to upload photos, which ultimately can be really cool if you can go to a site and see actual photographs. It's very inspirational. Use Twitter to send local alerts. We'll get tweets that are actually far away from the aurora, far south of the aurora, for example, in the continental United States. That's okay. What that means is that locally, for example, if you're in Utah, for example, you have a great view of the aurora, then people near you then could be alerted by this and go out and also see the aurora. And that's a great way to involve the public in this. Also, retrospective analysis that may be of interest to the scientific community more. And of course, we have to worry about quality control. Such issues, quality issues to consider, of course, false detections. There are several towns and cities around the United States called Aurora, so those are probably going to dominate tweets. Again, we can direct users to use a dedicated account. Lack of geolocation turns out, I guess based on the USGS experience, only about 10% of tweets have proper geolocation. So we just have to instruct people on our website, do this, this, and this, and you'll get your location, if you so choose, into your tweet. And of course, quality control that many people with this kind of a service face, blocking problem users, we can rely on user policing. That works well. For retrospective analysis, basically, we need to develop a way to store the information, to retrieve the information, to plot the information, either in the Google environment or another environment. Other possible NOAA PEEPs in the area of space weather, something that I'm personally very interested in, are space radiation-induced satellite anomalies. We currently have implemented a model that predicts, based on particle radiation measurements at another NOAA satellite, the GOES satellite, which you just saw some images from. It predicts the longitudes in that orbit, the geostationary orbit, where satellite anomalies are likely to occur based on these measurements. And in this case, we wouldn't rely on tweets from satellite operators, but rather internet-based forms that they could fill out anonymously, based on provide the location, the nature of the anomaly, if they so choose. And this was certainly probably have, in particular, a retrospective use. So other users who had issues can go and see, okay, well, this was the prediction of the model. This is where people actually had problems, and lo and behold, we had similar problems, and that helps them get into the root of their issue. And you start seeing this is actually a case of tweets during Hurricane Sandy running there. Just an example of another possible NOAA PEEP. Done by Stefan. It's waiting a little. There we go. So in conclusion, user eyewitness reports are an abundant source of free data. And in the case of the aurora, I see that we benefit a lot right now from various websites where people have posted their own images of the aurora. We like to harness that energy, that interest in the public, by incorporating their reports with our models, our science models, and treat these reports as an additional source of data. We think social media, such as Twitter, provide a very useful pool of user reports. And ultimately, combining models, data, and user reports will provide a more accurate, real-time validated final product. Thank you for your attention.
We have time for a couple questions.
That's a good question. As I understand the Aurora project, I think it would be pretty much limited to encouraging people to use the address, the dedicated address for this, so that we don't have to sift through mentions of Aurora, Colorado, for example, and also to provide, make sure they have their location in their phone. Otherwise, all they have to know is what the Aurora looks like, and so it's a bit self-selecting initially. But we hope that maybe, especially if this seems to be it's a great means not just for improving data but also for outreach. And I could just think of, for example, Stefan's peers participating in this. And I don't tweet, I confess. But I think the other age groups are more likely to do that, and but at least for the Aurora product, I don't think we want to direct them too much. I'm not sure if I'm answering your question properly there. I don't know if they've considered that. That's a good idea. I'll suggest that to them. I think certainly, a lot of people who will see the Aurora will be on the road, literally. It could be. So that's a good idea.
Thank you.
Yeah, thank you.
And our final speaker of this session will be talking about RSS.
Real-time mashup of Earth data and information through RSS feed correlation.
If you need to use the
Okay. So, hello everyone. I'm Na Chung. I'm a software developer at JPL, and our PI can't be here today, Andrew Bingham, so I'm taking his place to give this presentation. And the work that we've done is funded by NASA Access Project. So for today's agenda, I'm going to be talking about the challenges of finding data and information, and our approach of using data casting, which is a publish-subscribe mechanism to find data and information. And I'll explain the concept of cross-feed correlation and how it is accomplished through the use of the data casting feed reader software, as well as the data casting event viewer portal. So there's a lot of information, science data and information available on the web today. But the challenge is, how do we categorize and find these data and information for a specific event? So for example, let's say a massive earthquake struck and resource manager needs satellite data and imagery or images from eyewitnesses or damage assessment reports and really any type of data and information. So the challenge is, how do we help these resource managers or anyone looking for these data and information find them? So our approach is to use RSS, GeoRSS, and data casting RSS to create a mashup. Now, RSS feeds is a popular way for content provider to publish the availability of new content, such as sites like CNN or BCC publish the availability of new news articles. And GeoRSS is built on top of that to include a geolocation for each item, such as the latitude and longitude of an earthquake. And finally, data casting RSS is built on top of GeoRSS to contain science-specific metadata. So for example, it will allow you to specify the acquisition time period of a data file. So the idea is that RSS, GeoRSS, and data casting RSS feeds are widely available on the web. So we want to use these 3 types of feeds to create a mashup in order to find data and information and categorize them by a specific event. For example, a fire, a flood, or an earthquake. Here's an example of an RSS XML file. You have the channel elements which describe the entire feed, such as the title and description. And then for each item, you have a link to the resource and a description describing what the resource is. In this case, it's a link to a NASA news article. Here's a GeoRSS XML file, which contains everything that the RSS file contains, with the addition of a geolocation element. And in this case, it's the coordinates of a storm observation. And the data casting RSS specification allows you to, at the channel level, specify dataset related metadata, such as where's the source of the data files from. And at the item level, you can specify metadata specific to a data file, such as the acquisition time period of the data file, or even a URL to a preview image of the data file. So using these 3 types of feeds, we've defined what we called cross-feed correlation, which is basically the concept of using metadata that is in one feed to correlate that with metadata found in another feed. So in this diagram, for example, you can see there's a Google News RSS feed. I'll show. The Google News RSS feed, the Ocean Storms GeoRSS feed, and a Modis data casting feed that publishes the availability of the last 10 days worth of data file. So to illustrate cross-feed correlation, the first step is to identify the source feed. In this case, it's going to be the GeoRSS feed that contains the storm observations. So first, we'll use the published date of the storm observation to correlate that with the acquisition start date of the Modis data file. And then, similarly, you can use the published date of the storm to correlate that with the published date of the news article. In addition to that, we can use the title of the storm, which contains the storm name, to correlate that with the title and description of the news article. Finally, for the spatial aspect, we can use the location, which is the latitude and longitude of the storm observation, to correlate that with the location of the coverage of the data file. Now, when we correlate these metadata together, the output is basically a grouping of all the storms observations, the news articles, and the data files categorized by each storm name. So this correlation output can then be used to drive web applications or desktop applications. And in the example here, it's a web application that we've built. So to better illustrate cross-feed correlation and how it is accomplished through the use of the data casting feed reader, I'm going to present a use case. So let's say, for example, that a resource manager wants data and information for all recent ocean storms in the North Atlantic. And data can be anything from satellite data to in situ measurements, and information can range from anything to news articles or blog posts or assessment reports. So now that the resource manager knows that she needs to find such data and information, how does she go about finding these RSS, GeoRSS, and data casting RSS feeds? Now, for RSS feeds, there are websites out there, such as Feedzilla, that you can use to search for your feeds of interest. And for GeoRSS and datacasting RSS feed, what we've done is we've built a feed directory where data providers, such as data centers, can publish the availability of their datacasting RSS feed, and even if they have GeoRSS feed. So if you visit the feed directory, you can search for GeoRSS feeds from USGS that publishes occurrences of earthquakes. Or you can find datacasting RSS feeds that publishes availability of AIRS data files. So the first step to find the data and information is to first subscribe to the feeds of interest. So for example, in this example, we've subscribed to a Google News feed that publishes news articles about hurricanes, MODIS feed that publishes MODIS data file, and a GeoRSS feed that publishes storm observations. As you can see, these are the subscribed feeds in the panel, and the feed items for the selected feeds are shown here. Now, once you've subscribed to these feeds, you can, because our use cases, we only want the data and information for recent storms in the North Atlantic. What you can do is filter the storm observations by region. So for instance, here we've selected the North Atlantic. So all the items for the filter are hurricanes or storms only in the North Atlantic region. And furthermore, after subscribing to these feeds, you can download data files of interest and, most importantly, cross-correlate feeds. So the first step in creating a correlated feed is you have to identify the source feed, which in this case is the recent storm in the North Atlantic, which is basically a filter of the storms feed. And then you pick the feeds that you want to correlate the storms feed with, which in this case is the Google News feed and the MODIS data feed. The second step is, since we want these data and information grouped by the storm name, we have to identify how we want to categorize these data and information. And since the storm name is available in the title of each item, what we've done is we've selected group results by title right here. And then what you see is a preview of the recent storms in the North Atlantic. The final step is to identify how we want to map the metadata. So for example, in the recent storms GeoRSS feed, we want to map the location of the storm to the location of the MODIS data file. And we want to map the published date of the storm to the acquisition start date of the MODIS data file. And after, we have to do this mapping for every feed that you want to correlate the GeoRSS feed with. And after that's done, the result is basically a grouping of disparate items by each storm name. So as you can see, we named the correlation data and news categorized by storm. And if you select Hurricane Sandy, you see all the MODIS data file and the storm observation and news articles specific to Hurricane Sandy. Now if you select Tropical Storm, I think that's Tony, then you can see all the data file, news articles, and storm observations specific to the Tropical Storm Tony. Now, after you perform this correlation with this data casting feed reader, you can download these data files, you can read the news articles, and view the extent of the storm. Now, the result of this correlation, which is really just a grouping of files, can then be used to drive an external application. So what we've done is we've built a data casting event viewer, which utilizes Google Earth to create a mashup of satellite data, forecast information, and news articles categorized by natural event. And here I have an example showing Hurricane Sandy, the MODIS and AIRS data, as well as news articles. On the web portal, you can also see events such as earthquake, I think we have flood, and all the data and information that we have for these events. So to summarize, there's a lot of data and a lot of information available on the web, but the biggest challenge is how do we help people such as resource managers find and categorize these data and information. So what we've done is we use RSS, GeoRSS, and data casting RSS feeds to correlate the metadata, and the result is a grouping of these data and information. If you want more information, visit us at datacasting.jpl.nasa.gov. Thank you.
We have time for a couple questions. I've got a question. So how do you, like, is there a way for people, you know, well, first, I guess, is there a way for people to, you know, access this capability in a way where they can evaluate which feeds they're going to, you know, be, I'm sorry, I'm having a hard time seeing.
It's okay.
Having a evaluate the feeds or the quality of the feeds? Or is that just a self-selection?
It's really a self-selection. So if there are lots of GeoRSS feed, for example, that publishes occurrences of earthquakes. So the user will have to either look at the feed and verify that that's really the feed that they want. Same for data feeds and such. The question is if there's any quality in the ranking of the actual items published in the feed. So there's no quality ranking. Basically, the feed reader returns all the news articles that it thinks, based on a certain criteria, is related to Hurricane Sandy. And it's up to the user to filter out what news articles the user is actually interested in. But with this capability, it helps narrow down the search by a lot because it filters the news articles. Yeah. The question is, to what extent do we curate the feeds for the feed directory? For the feed directory, we allow data centers to basically fill out a form publishing the availability of data feeds. And then we have someone who actually go through to look at the feed and make sure that it contains valid information. And to further explain that, so for GeoRSS feed, we actually created a crawler to crawl for GeoRSS feeds on the web. But again, we have someone who verifies the GeoRSS feed before we make it publicly available.
Thank you very much.
Thank you.
So this concludes this portion of this session. We're going to have a session tomorrow morning on, I guess, more looking at the use of near real-time data in space weather applications, followed by some Earth science applications at 10 o'clock, and that's in room 220 in Moscone West. And we'll have a poster session in the afternoon. Thank you all for coming, and I guess it's time for beer, so I know a lot of people are running.